Hi, welcome. In today's video, I'll show you how to find the eigenvalues and the eigenstates of a given operator once you have the matrix representation of that operator. Let's find the eigenvalues and eigenstates of the operator Sx. We have the following matrix representation. First, I'll determine the eigenvalues through the general eigenvalue equation given by Sx. Let's assume a general ket alpha equal to alpha ket alpha. I'm assuming here ket alpha is the eigenstate of the operator Sx and alpha is the eigenvalue. So the possible eigenvalues alphas are found through the secular equation that is given by this expression here. So the determinant of this matrix within this modulus must be equal to 0 to provide you non-trivial solutions. This is simple to calculate because you know the matrix representation for Sx, and this I here is the identity matrix. Therefore, we have these are the eigenvalues of the operator Sx, and plus and minus h bar over 2 were to be expected, as we know that the only possible results of a measurement of any spin component are plus or minus h bar over 2. Now we're ready to calculate the eigenstates of our operator. First, I'll do for spin up. We have this eigenvalue equation for the operator Sx. I will assume here a general ket plus subscript x as A and B represented by this matrix. So we already know the matrix representation for the operator Sx. Then we just plug all the matrix into this equation, and we have, according to our system, A must be equal to B, and for simplicity, the simplest non-trivial choice is A equal to 1, therefore B will be equal to 1, and then our eigenstate along the x direction is represented by this matrix, and if we normalize it, we end up with this eigenstate. Same steps for ket minus subscript x, the other eigenstate of our operator, and I write down the whole calculation, which is, and of course here I assumed that ket minus subscript x has also this representation, and from here we have that b equal to minus a. As before, for simplicity again, I will assume a equal to 1. It implies in b equal minus 1, and our ket minus subscript x is represented by this matrix, and if we normalize it, we end up with this representation. These eigenstates were to be expected either, as you can check in the previous video. So in this example, we learned how to find the eigenvalues and the eigenstates of an operator from its matrix representation. That's all for this video. Thanks. Bye bye.